Alright guys, welcome. Today I'm going to be going over solutions for the 2D electron gas. Now everything I say here can be just as easily applied to the 3D electron gas. However, I'm only going to go over the 2D right now. So first off, what is a 2D electron gas? The 2D electron gas is a gas in two dimensions of electrons. No reason to complicate it anymore than that. Now this gas, we're going to assume, is a perfect sphere that has radius kf. Well, the reason why we assume that its radius is kf is because, fun fact, we're in k space. We got kx and ky. Now, those of you who will remember from going over reciprocal vectors will remember that in k-space and reciprocal lattices, we have our units in 2 pi over a. There's one thing I want you guys to remember, because it'll come up here in a minute when we're going through the derivations. So one of the very first things that we're going to want to find with this 2D electron gas is, well, the number of electrons. So I was going to write that here. And, well, how are we going to do that? So the very first thing we're going to be doing is taking this in steps. So we find, if you think about it, the area of our total 2D electron gas divided by the area per state of each electron, we're going to get the number of states. So if we go back up to my drawing here, each state is like one of these boxes I'm drawing, right? So if we take the number of boxes that fit in the circle, we're going to find the number of states we have. That's great and all, but that's not quite the number of electrons. The number of electrons is twice the number of states. Now, if you guys are wondering where this 2 comes from, right it up here, comes from Pauli's exclusion principle. So those of you guys who don't remember, Pauli's exclusion principle says that in every state there can be one spin up and one spin down electron. So if every single state in this 2D electron is filled, every state will have 2 electrons, thus maximizing the number of states we have. So, moving on. Well, now we're gonna have to calculate each of these values. So, I will start with the area of states, and I'm gonna actually do this in a different color for you guys. So blue. So area over 2D EG is equal to pi kf squared, because kf is our radius of our circle, so pi kf squared. So we'll just highlight this in blue so you guys can see where that's coming from. And highlight this next part in red. I will write this in red. So the area per state now this is where the units of 2 pi are going to come in, because each side of one of these states is going to have 2 pi over L is their length, and since we're talking about squares, we're just going to square that, and we're going to write this as 4 pi over A, where A is equal to L squared. So A really just represents our area. No reason to complicate things. So going back to the black pen here, our number of electrons is going to be pi kf squared, over 4 pi times our area, all multiplied by 2. So, going on to the next page. Oh, there it goes. We are going to get n, our number of electrons, is going to equal area times kF squared over 2 pi. And here is the first thing that's important. So now that we found the first thing that one of the first things we're looking for, the next thing we're going to be looking at is our density of states. Now this is equal to the derivation of the number of electrons with respect to their energies. So we're kind of at a loss here, right? Because the number of states is in terms of kF, not EF. So how do we get this to be n of EF? Well, there's an equation which states that our Fermi energy is equal to h bar squared over 2m times kF squared. So if we solve this equation for kF squared, we get that that is equal to 2m times our Fermi energy over h bar. So we can plug this into our number of states. So our number of states in terms of our energy is now equal to, I'll just keep our area over 2 pi here, and we get 2m EF over h bar. Doing some simplifying, just canceling out these 2's, we get that is equal to am, so Fermi energy, for pi h bar. So if the density of states is equal to dn dE, this is now equal to am over pi h bar. I'll also box this in green for you guys. So one thing that you guys will notice, and it's right in black here, is that this does not depend on energy. And the reason this does not depend on energy is because we don't see any E terms. So if we saw something that had an E term in here, it would depend on energy, but the density of states, at least in a 2D electron gas, does not depend on energy. This would not be the same sort of case with a 3D electron gas. However, this is the case with our 2D electron gas. One mistake I realized after going back through this, when I was showing you guys how to do this, is that I didn't originally put h bar squared in the numerator for the Fermi energy. You'll notice that every time I highlight in purple here, I fix where there should be a squared for h bar squared. Sorry for this, guys. Realize this in post editing. So from here, we're going to find our energy at 0 Kelvin, or absolute 0. So our equation for this is the integral from 0 to our Fermi energy of epsilon times our density of states with respect to epsilon. So we're just going to plug in our density of states equation. So we got U is equal to 0 to EF of E, and our density of states was AM over pi h bar squared. And we're going to take this with respect to epsilon. This integral comes out to be 1/2 8m pi h bar squared times EF squared. Now, if you guys remember, n is equal to AM pi h bar squared times EF. So we can simplify this down and say U is equal to 1/2 N times our Fermi energy. And this right here is our energy at 0 Kelvin. And one thing I do want to make a note is that right here, if we simplify down to this step, it makes it easier to read. So that may not seem like much, but if you get in the habit of making things easier to read, it will help you in the long run, because you will find out that a lot of textbooks, well, when they're talking about, you know, like a 3D electron gas, and other people are talking about it, they'll simplify it, and a lot of times that means bringing this N term back inside their energies. So hope this video helps you guys who are struggling, and good luck.